So good morning, everyone.
Good morning.
So today, yes, I haven't written in short. Perhaps I should have written in detail. Today we are going to start with the topic of moving coil galvanometer. Galvanometer is a device which measures current, and this can be converted into ammeter as well as voltmeter, which will follow this particular topic. Okay. So, but before we get started with this topic, I think some part of torque and what we were doing earlier, one or two questions were left. I thought we'll deal with those questions also. So first I will take up this question. What is the question? Let's assume what is this? This is a sphere, and on a sphere, whatever sphere is mass is m, radius is r, and we have wound a coil around this sphere. This is something is running in this coils are wound in a horizontal plane. Okay, so coils are wound in horizontal plane and current I is flowing and n number of turns are there. Okay, and if we switch on and this surface is rough, so we'll take one by one two cases. First case, what will happen is surface is smooth, and moment we switch on magnetic field, what will happen when we switch on magnetic field here?
There'll be a rotation and
so let's try and understand. There are two ways to understand. One would be, as soon as we switch on the magnetic field, first of all the current is flowing, so front side the current coil is going like this, back side will go in the other direction. If you have to mark the direction of magnetic dipole moment using right hand thumb rule, magnetic dipole moment will be in vertically upward direction if coils are in the horizontal plane. This would be the direction of magnetic dipole moment. And if I take this, so what will the value of magnetic dipole moment? Magnitude is number of turns into area and IA. So n into current is I and area is pi r square. That is a magnetic dipole moment. So moment is switch on the magnetic field, torque will start acting, and we know the magnetic dipole moment will try to turn in a such a way so that it comes and aligns with the magnetic field. So which will tend to rotate? It will tend to rotate about an axis passing through center mass and perpendicular to the plane containing m vector and b vector. It will rotate about an axis passing through center of the sphere, and this is axis we see from here. It will tend to rotate. So the question is, first of all, what torque will act on the sphere? The torque acting on the sphere will be what? So torque is easy to calculate. Angle between them is 90. So magnitude of torque will be equal to m into b, and sine theta will be 1. So this is torque which will act, and I pi r square b. So what is this torque to do? One way of thinking the torque is trying to rotate in this fashion. Right? You can think of torque is something like this: some forces acting downwards and some forces acting upwards. Net force is 0. But what is trying to do is trying to rotate the whole sphere. What will happen if the surface is smooth? What will happen if the surface is smooth? And what will happen when the surface is rough? So let's take both the cases. What happens when the surface is smooth? So when it is trying to rotate, and if the surface is smooth, what are the forces acting? Forces acting will be equal to weight downwards here, and normal reaction also will be equal to, since it is not having any displacement in the vertical direction, acceleration vertical direction will be 0. So n will be equal to mg. So this is the only torque which is acting. So when you take torque about center mass, this is the only torque which is acting. These two forces will not create any torque about center mass. So in this case, it will have angular acceleration at this particular value. What is value of alpha? Alpha is equal to tau by I. Thus a instantaneous value of angular acceleration. Will it remain constant? No. As it rotates, what will happen? As suppose it has rotated, and so it will start rotating at the same point. Center mass also will not shift. So at the same position, it will start having rotational motion, pure rotation about axis passing through center mass and perpendicular to plane containing m and b vector. It will have angular acceleration. What will happen if the surface is rough? If the surface is rough, see, because of angular acceleration, so this still try to rotate, and this point also, if this is value of alpha, suppose only rotation is happening. And so this point at different points of the object, this point will have an acceleration equal to r alpha. So this point, which is in contact with the ground, will tend to have acceleration in the backward direction. If the surface is rough, it will try to keep these 2 points together. So if it is trying to get develop acceleration in this direction, it will oppose this tendency for slipping. No slipping is started. It will oppose the tendency of slipping by applying a friction force in the opposite direction. So moment the surface is rough, friction force will start acting. And if the surface is rough enough, this point will have zero acceleration, the point P. So how much friction force will act? So moment surface is rough, F will oppose tendency for slipping tendency. So if the surface is rough enough, that point P will still remain at rest. If point remains at rest, which way, how would this sphere move in that case? We have done this case, any object if it is not slipping. So this point will remain at rest. Whole sphere, it will behave as if it is rotating about a fixed axis passing through P. So at an instance, if the surface is rough, so sphere will have rotation about which point? About P. At the particular instance. So can we calculate what will so if it is having rotation about this point, then what is the alpha here? Will the alpha here, so will it still have alpha? Yes, it will rotate. It will tend to rotate about this point. What will the alpha in this case, in case of rough surface? Has the torque changed? Torque has not changed. But here it is rotating about center mass. Here it will rotate about point of contact. And axis passing through P perpendicular to the plane. Only thing which will change now, here in this case of rough surface, since it is rotating about point P, moment of inertia also have to take about point P. So what will happen? Torque will remain same, but moment of inertia about an axis passing through point P. So I have to apply parallel axis theorem. It will be ICM plus MR square, which will be equal to, so IP will be equal to IC plus MR square, which will be equal to IC is equal to, if it is sphere, 2 by 5 MR square plus MR square. So I substitute, which becomes equal to 7 by 5 MR square. And accordingly, I substitute here, I get an alpha. So this is how it will behave in these two cases. Okay. Now coming to this question here. What happens if a spherical kind of shape, this shown figure, coil of single turn, number of turn is single, wound on a sphere of radius r, mass m. The plane of the coil is parallel to the plane. So this coil also is inclined. If coil is inclined, it means magnetic moment will be perpendicular to the plane of inclination. And it lies on the equatorial plane of the sphere. Current I is then the coil. Find the value of B if the sphere is in equilibrium. Which is direction of B? B is this direction. B is vertically downwards. So which way, first of all, what should be direction of M vector for sphere to remain in equilibrium? So condition for equilibrium, what has to happen for condition for equilibrium? So all this question are basically rotation motion question. So
Sir, it's rotational equilibrium.
yes, of course, but the equilibrium is rotational equilibrium.
Okay.
It has to have
Still slides
transmission
down,
as well as
right?
rotation. So what will happen if I draw the free body diagram slightly larger here? So this is the plane inclination. It is kept on this plane at an angle theta here, and this is where how the sphere is. Okay. So at this point, what are the forces which are going to act? So in this case, if we look at, will it be in rotational equilibrium? If this torque was not acting, it would have linear acceleration in this direction. It will also have an angular acceleration in this direction. Now for equilibrium, first of all, if I think of rotational equilibrium, it means some torque has to act. Now this torque, earlier the torque was acting in this direction, it would have rotated in a clockwise sense. So torque must act which is in anti-clockwise sense. Then only you will get a rotational equilibrium. So first thing what I understand, I'm going step by step. So which way the torque due to magnetic field and magnetic moment should act? It should act in which direction? It should act in this particular direction. So what is the value of B? So should I have M value to M, two directions are possible. M has to be perpendicular to area of the coil. So M could be depending on current direction, either M could be upwards like this, or it could be downwards like this, depending on the direction of current. So should it be upwards or should it be downwards for rotational equilibrium? If it is upwards, this is B vector and this is M vector. So what is M cross B direction? M cross B will be this direction. If M cross B direction, what is the torque? Which direction the torque is acting? Torque is acting in this case clockwise sense. Do we need the torque in clockwise sense or do we need anti-clockwise sense? We need the torque in the anti-clockwise sense. So first we have to understand M2 has to be in such a way that if M2 current direction should be such that magnetic moment is in the downward direction. So that we can find the direction of current. If it is in the downward direction, now coming to what is this torque equal to? This torque will be equal to, what is the torque here? What is the angle if it is downward direction? What is the angle between M vector and B vector? So torque will be equal to, so torque due to magnetic forces is equal to mb sine theta. Sine theta being the angle between M vector and B vector. What is the angle between M vector and B vector? B vector is vertical and M vector is perpendicular to inclined plane. So this angle also will be what? What is this angle? This angle also will be theta. So torque will be equal to mb sine theta. Okay. I will calculate M. M is equal to, what is M a value equal to? Single coil. So I into pi r square B sine theta. Okay. Now, how do I equate this torque to? I need one equation to find a solution for this. So in this particular case, whenever it is in equilibrium, I could equate torque about any point. Should I equate the torque about point C or should I equate the torque about point P? So if I take this one, there are two ways of solving this question. If I draw the free body diagram, what are the forces which are acting? I can mark this force equal to, what is this force? If I take this component, this is equal to mg cos theta, and the inclined this direction is mg sine theta, and normal reaction will act, which also will equal to mg cos theta. So how much friction force must act for it to remain in equilibrium? Can we identify friction force? What must be equal to friction force for it to remain in equilibrium? Yes, if I look at along this, if I take this as x and y direction, along the slope mg sine theta is acting. So for its equilibrium, friction force also has to be equal to mg sine theta. That's the friction force. That's the friction force which must act for this to remain in equilibrium. Now, what is the condition for rotational equilibrium? I can take torque about this point to be 0, or I can take torque about this point to be 0. Which one should I take? I think it's much easier to take torque about this point is 0, because torque of normal reaction as well as friction force becomes 0. If I take torque about this point is 0, what is the torque due to mg sine theta? Torque due to this component of this has 0 torque. Mg cos theta is passing through point P. So if you equate torque, okay. So if you equate torque about point to be 0, if I take summation of torque about point P to be 0, there are, of all the forces, mg sine theta, mg cos theta, normal reaction and friction, only one force is non-zero torque, which is mg sine theta. Its perpendicular distance is r. So torque due to those gravitational forces mg sine theta into r, that torque has to be equal to torque created by magnetic dipole. That has to be equal to I into pi r square b sine theta. So this is the condition for it to remain in equilibrium. What is the value of I? We can find the value of I from here. What is value of I here? Sin theta gets cancelled. I is equal to RR1 gets cancelled. Mg by, okay, suppose you have to find the value of B. Value of B is equal to Mg by pi I. That's the answer. Okay, so this also is a question on rotational equilibrium. So, okay, so those who understand rotation will find it okay to understand. Otherwise, it's little not entirely the topic of magnetism. It is a multi-concept question, requires understanding of rotational equilibrium as well. Okay. Now I move on to the topic of moving coil galvanometer. This topic relatively simple because this topic does not require any cross product and all, and it's important topic. The questions on this topic are fairly simple, and everybody should be able to solve this question without much of difficulty. So what is a moving coil galvanometer? It's a very sensitive device to measure small currents. Let's say some of the very sensitive galvanometer which are made can measure current even something like 1 nanoampere. Very small value of current also can be measured. Okay. So it's a very sensitive device, very small current also it can show deflection, it can measure. Okay, and which principle does it work on? I will draw a parallel. See, or for some of you may know, even a spring balance can be used to measure weight. Which principle does the spring balance work on? So try to see what is the parallel between the two. It is similar to measurement of weight using a spring balance. In case of spring, what happens when you suspend any mass which has mg weight acting downwards? Weight is counterbalanced by spring force. And what is spring force is equal to? So weight becomes equal to K into X, X being the extension of the spring. So how does it give you weight? So X here, so what is that? Rather than measuring weight, what are you measuring? We are measuring actually extension of the spring. So when X varies linearly with weight, hence measurement of extension gives you the weight to some scale. So what does it imply? If I suspend 1 kg weight, it has from equilibrium position, if I suspend 1 kg weight, it has particular displacement in vertical direction X. If I suspend 2 kg weight, it will become twice as much. If we have 3 kg, thrice as much. So by measuring extension of the spring, which varies linearly with weight, I can measure weight. So this is the common principle we use for measurement of many physical quantities. We have seen earlier. So rather than measuring the physical quantity, we measure something else which has a linear variation and we can correlate between the two. So here also something similar. Let's try and understand how does this function. The overall approach is similar, but there's some similar, there's some difference also. So let's see how does it work. So first of all, I think the figure is not okay. This is the figure. These are the two. This is a magnet. This is the north pole of the magnet. This is the south pole of the magnet. Okay. So in between the magnet, there's a magnetic field. And what kind of you see the shape of the magnet? Mostly you have seen the shape of the face, plane shape. Here, this magnet surface is like a concave, and we also call it the shape of the magnet is like a horseshoe. And this is what we use is using a horseshoe shaped magnets. And in addition, why do we use a horseshoe? Because magnetic field is perpendicular to the surface. Similar to electric field, we'll come to that again later. So moment we take as a concave, the field becomes like a radial field. So we use horse-shaped magnets or concave-shaped magnets so that field becomes radial in direction. That's one reason. And second thing, what we do, in addition to using concave-shaped magnet, we place an iron core in the center. This iron cylinder kind of thing. What does iron do? Actually, iron also attracts field lines. So it makes field lines more concentrated, increases value of magnetic field. It also makes the field lines radial. So the two things we do to make field lines radial. One, use of concave shaped magnet, and second, using iron core. Both things put together makes the field line radial in direction. We'll see what is the advantage of radial field direction. Okay. Okay. So a coil is placed and radial and uniform magnetic field. Where's the coil here? We see this is iron core, and what is it? This is a coil. So it's a kind of rectangular coil which is wound on a cylinder. So this cylinder, we place this coil. So these are the coils here, multiple turns. Okay. So these coils are placed in a radial uniform magnetic field. So where is the coil field? If these coils are placed like this, magnetic field lies in the plane of the coil. All of you can notice coil lies in the radial direction and field also is in the radial direction. Magnetic field lies in the plane of the coil, which means angle between M and B is 90 degree. So even from this angle orientation, suppose the magnetic field it rotates, it comes to some other orientation. Whichever orientation this coil is, in any orientation, since the magnetic field is radial, angle between M vector and B vector is always 90 degree. That's the purpose of keeping a radial field. I'll repeat again. How is the coil? Coil is placed in between coaxially. So what will happen? So whichever direction the coil direction is in the radial direction, and since the field line also in the radial direction, field lies in the plane of the coil. If field lies in the plane of the coil, magnetic dipole moment being perpendicular to the plane of coil, angle between M vector and B vector is 90 degree, torque is MB sin theta being 1, torque is always M into B. That's the advantage. So coil is placed in radial uniform field. Radial field ensured magnetic field lies in the plane of the coil for any orientation within a particular range. Suppose it deflects too much, it will not be radial. There's certain range, so up to a particular deflection, up to a particular angular rotation, the fields are radial, and within that, this condition will apply, which is called within operating range. Okay. When current is passed through the coil, this is a coil here. When the current is passed through, what will happen? It will develop a magnetic dipole moment, and if the current becomes double, magnetic moment dipole moment also become double. So when the current is passed through, this coil becomes a magnetic dipole, and it is a magnetic dipole placed in a magnetic field, which is perpendicular to direction of dipole. It will experience a torque. It will tend to rotate. Suppose it is tending to rotate. So what is the torque it will experience? It will rotate, and since the angle between M vector and B vector is always 90 degree, torque will remain constant and will equal to M into B and IAB. This is the torque which will rotate this coil. What you see here, see something, the way you have a spring here, there's something called torsional spring. You will see the torsional spring, some of the toys around, we've seen something, it is like a spiral kind of shape. So its rotation is resisted by a torsional spring. Torsional spring has some properties similar to normal spring and some properties which are different. In case of normal spring offers a resisting force which is proportional to linear displacement. Torsional spring offers resistance to rotation. So it offers a torque in form of resistance, and resisting torque is proportional to angular displacement. So here F is equal to Kx in case of linear spring minus X, because to indicate opposite direction. In case of torsional spring, it offers a resisting torque which is proportional to theta, or resisting torque offered by torsional spring is equal to some K times theta. And K term here is called torsional constant. Here it is spring constant, it is a torsional constant. What was the unit of torsional constant here? K is same unit as unit of torque divided by theta. Unit of torque is Newton meter per radian. That's a torsional constant. So what will happen so there are two torques here. One is rotating torque, one is resisting torque. It will come to a state of equilibrium where two torques become equal. So what is the condition for equilibrium? In the equilibrium, rotating torque will be equal to resisting torque. So this is the only important part of this, what he had done so far. We equate two torques. This torque is rotating torque. Why the sin theta term is not coming? Because any orientation within a particular range of angular displacement, the angle between M vector and B vector is 90 degree because of radial field. So even as the coil rotates, torque NIAB remains unchanged due to radial nature of field. So that's the equation we get here. So hence, what is the current here? What is current? If I write it, current is K theta by NAB. And what we notice here, current is directly proportional to theta. What does it mean when the current is directly proportional to theta? So it means, suppose I have an angle here. So this is something, as this rotates, this pointer also will rotate. So if the current is say 1 microampere, I get a deflection of say 20 degree. If I make the current half, angular deflection will be half of it. If I make fourth, angular deflection will be 1/4. So once I mark the reading for a particular value of current, Later on, I can have graduation which is uniform, a linear kind of graduation. Okay, so all graduations are equally spaced, and we can have the marking done on the dial, and that's how it works. So current is directly proportional to theta, and we call something called sensitivity. Let's try to understand sensitivity. Sensitivity is angular displacement per unit current, theta by I. Then we'll try to understand what does this imply. Sensitivity is equal to NAB by K. So what is sensitivity? See, sensitivity, just imagine, so suppose there are different weighing machine. There's a person of 100 kg per person, 100 kg, a really heavy person. So there's a, if you see the weighing machine, what you have at home, so you have some reading, and those which have a needle kind of thing. The person gets onto the weighing machine, it may deflect by 90 degree, whatever, okay. And you see there's some weighing machine, if you go to something like railway station, you'll have weighing machine which can measure heavy weight. So here what will happen, it gets, same 100 kg person gets on the weighing machine and we find the angular displacement is very small, because that machine can measure up to 1000 kg. So what will happen in this case, theta is large, here theta is small. This is theta 1 is large and theta 2 small. Among the two machines, which machine is more sensitive? Which is more sensitive to weight? The one which has larger displacement for the same weight is more sensitive. So sensitivity is measured. So that's the reason of sensitivity, how sensitive the machine is. This I have given indication of sensitivity to weight measurement. And similar way, if we can measure sensitivity of galvanometer in terms of angle by which it deviates or rotates by current value. So, and that sensitivity is equal to NAB by K. If I want to have very sensitive galvanometer, which means it should have significant angular displacement even for a small current. How do I make it very sensitive? Numerator should be large and K should be small. How do I make the numerator large? What is N here? Number of turns. So I'll let a rotator have more number of turns connected to the coil here. But only problem with increasing N is, as increasing number of turns, length of coil is increasing and the resistance of coil is also increasing. And you know, when the resistance is there, when you pass current, it leads to heating effect. So I can increase N. How do I increase A? So I can have, if I have a large area of cross section, so I use a large, slightly larger kind of cylinder here on which I want the coil. More importantly, third part. So when making large, also instrument becomes large. So when I make N large, problem is N large is what? Length of the coil becomes more, resistance becomes more, heating effect takes place. Area making large, problem is if you make the area large, the instrument becomes large in size. Third thing is magnetic field. This is something, how do we make B large? By having a strong magnet. And we can make this strong field even larger by having an iron core, which we'll deal later. So if we have a material, iron core has a property of increasing the magnetic field many times, hundreds of times more. So B is increased by having a strong magnet and using an iron core. Okay, and what is K? K should be as small as possible. So what is K as small as possible? So you know, like a linear spring, you can see spring what you use for measurement of weight. You would have seen the spring what is there in the car shock absorber. The car shock absorber, if you keep some weight, it will have very small linear displacement. Why it has very large, small displacement? K is large. And spring which is very flexible will have small K. So this spring also should be very flexible one. Very small touch, very small torque also, it should allow large displacement, angular displacement. So this is how we can have large sensitivity. Okay, this we are discussing this minor points. Major point here, or whatever, only point what he has so far is this. It works on this principle. You equate two torques. This is the torque which is rotating due to magnetic field, and this resisting torque due to torsional spring. Based on this, we get this equation. We get the sensitivity, and moment since I is proportional to theta. By measuring angular display, by measuring theta, we can measure current. That's the principle on which moving coil galvanometer works on. And as I mentioned here, with the known devices, it's possible to measure even very small current. Okay. So we have also discussed what are the ways we can improve sensitivity and what are the implications. Okay. Both high and small K to greater sensitivity. Okay. What it does again, another way to show this current, and this is something like this. red color, what you see is the coil which is wound. What is this circular thing what we see here? What could this be? We see circular cross section actually is a top view of a cylinder. And this is nothing but an iron core. This is an iron core. What shape? It's the shape of a cylinder. And there are windings which are of course insulated so that it runs windings run like this. And as the current is passed, if the current becomes more, M becomes more, torque becomes more, it start rotating, it suffers angular displacement. And this is, what do these things indicate here? Like a spiral thing kind of. This is the what you call as restoring spring. This is to be spring which opposes is rotation or angular displacement, and torque exerted by the restoring spring is K times theta. Okay, and greater the current is, greater the angular displacement, and greater it will be the deflection of the needle which is attached to the iron core. This is how it functions. What is the least count will correspond to? The least measurement is, this is something what is one reading, you can easily find least count. Least count is current corresponding to smallest angular division. Okay. Problem with high degree sensitivity, it is if you make it very sensitive, the maximum value of current that can be measured or the maximum value of current that can pass through the galvanometer becomes very small. Okay, so suppose I get a full deflection. Okay, I have made it very sensitive. How do I make it very sensitive? It gets full deflection for very small current. So even for 1 milliampere, it gets full deflection. So what it means, can I measure a current greater than this? I will not be able to measure a current which is greater than this. But whereas in day-to-day life, we come across currents which are much greater. In fact, home also, typical appliances, though it is AC current, but in terms of magnitude, there are order of 5 or even 10 amperes, which is common. So problem is, we have a moving coil galvanometer. That's a shortcoming. That's a limitation it has. If we have high degree of sensitivity, it limits the maximum value of current that can be measured or allowed to pass through the galvanometer. And we use the term IG to indicate currents going through the galvanometer. Okay. And why can't we have large angular deflection? Angular deflection should be such that it is within the radial range of magnetic field. We cannot have very large. You cannot have a 90 degree or 180 degree angular displacement. In that case, field will not remain radial. Okay. Graduations are equally spaced. Okay.
So we can use a resistor to increase the we can use a resistor to increase the maximum current to be measured, right?
No, but this is what will happen if how do I increase the resistor changes? Does resistor current changes current?
I mean, less current goes to the galvanometer.
Typically, it is measuring. See, it is measuring the current which is being fed to. Whatever current is being fed to, but suppose this coil, it gets this deflection at 1 microampere. It means I cannot have this current more than 1 microampere. If current is more than 1 microampere, it will have more than this deflection, which will not within the operating range. It doesn't matter, but this is current. I can see what you are saying now. If I connect a high resistance, I can lower the current. But what do I gain by lowering the current? Still the current which is being passed, which is being measured, is the current which is entering the coil. There's some other way. We'll come to how do we increase its range. That's a challenge, and that's something which comes as a part of the next topic. So first, in this topic, what you have done, if only thing I have to remember, what is the key of moving coil galvanometer? If I look at one sentence, what is the key point in moving coil galvanometer? What is the key point here? Disha, what is the key point here in moving coil galvanometer? What do you think is the key point? Disha, can you think of what is one point you have to pick up from whatever discussed last 10-15 minutes? Which one point is the most important one about moving coil galvanometer?
So like the torque created due to the magnetic field and the
due to torsional spring. That's
yes.
the only thing. So basically, so only thing MB sin theta, MB is equal to, that's the only point. That's the key point here. And why are we not using the angle? Second point, when I write this one, this is MB is equal to K theta. And then I can write value of M. But why I'm not using sin theta here, Disha?
Because the angle between them is 90 degrees.
90 degrees. And that's a radial field nature. That's the only thing what we understood. Okay, and that's all you can fill up. And then we write, that's the only key point here. So moment I think of moving coil galvanometer, this is the point we should come to mind. There's a torque which is trying to rotate, and there's a torque which is trying to resist angular displacement when both have become equal. Now we can fill up this value. What is M equal to NIA? NIA B is equal to K theta. That's all. And what is K here? I think we need to understand a little bit of torsional spring. Torsional spring, it offers a resisting torque. Resisting torque is proportional to angular displacement, and K value will be Newton meter per radian. So try to understand this one. So let's look at a couple of questions based on this topic. There's only one thing here. Moving coil galvanometer, so has 200 tons, resistance 100 ohms. Another meter B has 100 tons, resistance is 40 ohms. All other quantities are same in both cases. What is the current sensitivity? So two coils, one is 100 tons, 100 ohm resistance. Second one, what has happened? See, what if we try to visualize this question, what has changed here? See, what has changed? Rest all this magnet has kept same. Only thing, this coil has been replaced by a different wire. First case 100 tons, second case other number of tons, and if we replace the coil, resistance also will change. Okay, this is what is given. What is the current sensitivity? Again, if I don't recall anything also, I can start from very basic. I'll write what is current MB is equal to K theta. What is M is equal to NIA? B is equal to K theta. Current sensitivity is angular displacement per unit current, which is equal to NAB by K. Now look, which things is changing here? Is the area changing? Is the B changing? Magnet is not changing, B is not changing. The spring is not changing, K is not changing. Area is not changing. Resistance doesn't come into the equation anywhere. Only thing changing is N. So what is the sensitivity? First case and second case sensitivity will be proportional to N1 by N2. That's all. Number of turns. By increasing number of turns, if I make the number of turns double, keeping everything else same, the sensitivity become double. Okay, so sensitivity, that's a direct calculation. So current sensitivity, B has half number of turns. The sensitivity of B also will be half. A will be 2 times the sensitivity of B. So what does it mean? Same current is passed through this galvanometer. If A is there and B is there, both are there. So this is galvanometer A, and this is galvanometer B. If same current is passed through, if B has this kind of deflection from here, B need to deflect this much, A will deflect twice as much. So if this will be theta 1, this will be twice of that. That's a twice sensitivity, 200 tons. Can you experience twice as much torque? Okay, so we understand that part. Okay, let's read this question. These are also very simple ones. What is the current sensitivity of galvanometer? So by now we have seen, again, we can start from basic, or we can say what is the current sensitivity is equal to N into A into B by K. That's the current sensitivity, theta by I. So all this is pretty simple. It's 100 tons. Area is equal to 1 into 10 to the power minus 4, all SI unit, 5 Tesla. And this, what is this term here? This is the unit of K, torsional constant. And this is also an SI unit, so no problem. You can just substitute as it is. That will give me current sensitivity. In which unit now? If I write something like this, what is the unit I'm going to get here? Theta by I. This will come in radian per ampere. Theta by I, radian by ampere. But if my option in terms of microampere, how do we convert into microampere? Ampere I have to convert into microampere. 1 ampere is equal to 10 to the power 6 microampere. Okay, so again multiply by 10 to the power 6, we can convert. You can easily solve this question. So they are very simple ones. Let's look at see the issue what we have come across. Yes, it is very sensitive, but it so ammeter is a device. So what we do, how we convert into a actual working ammeter. If I have a galvanometer, how do we convert into a usable working ammeter? If it has to work as an ammeter, its range should be more than or equal or more than current we wish to measure. So what is ammeter? Ammeter is device to measure current and measure current in any part or branch of electric circuit. It is connected in series of the branch where current is to be measured. So let's understand, suppose this kind of circuit is given. If I want, what are the different values of current here? See, this is something, let's see, if this current is I1 here, it branches out, this may be I2, this may be I3. So all parts have different current here. And again, this part will become I1. So what are the different values? If I might want to measure this current here. If I want to measure current in the main branch here, how I have to connect? In this case, ammeter has to be connected here. If I connect ammeter A1, it measures current I1. If I want to measure current in this branch, ammeter has to be connected in series in that branch, A2. If I connect A2 like this, it will measure I2. If I connect ammeter A3, it will measure current I3. That's what is mentioned here. It is connected in series in the branch where the current is to be measured. This is how we connect. Okay. What is the limitation of Galometer? There are two limitations of Galometer. Let's understand each one of them. First of all, what you notice, practically range is too small. How do I measure current which is greater than its range? And second thing, see, since we have so many coils, why we make so many coils, number of turns are many, because we want to have high sensitivity. Its resistance becomes significant. So moment I connect ammeter anywhere in the circuit, if this ammeter has significant resistance, it alters the resistance of the whole circuit, alters the current. So it is supposed to measure the current, but it also the current which is supposed to measure. So even if it measures the current properly, but it is measuring altered current. So what is necessary? We had discussed this point in case of current electricity also. What should ideally happen for current not to change? Ammeter resistance should be as close to zero as possible. So these are two problems what we face. So we take some corrective measure, and the corrective measure is called conversion of a galvanometer into ammeter. How do we connect it? Let's try and understand its significance. Okay, so suppose this is a current I want to measure. What we do is just take an example. We'll try and understand in terms of example. So limitations are overcome by connecting a small resistance in parallel. Because whenever I want to reduce the resistance, what is the way to reduce resistance? By connecting a small resistance in parallel. So we connect a small resistance in parallel, and that parallel resistance is called a shunt. And when we connect up, what happens? If a galvanometer coil has resistance G, if I connect a shunt here, which is much lower than resistance of G, the effective resistance for the whole arrangement becomes even smaller than shunt resistance. That's the property of resistance connected in series. That's one thing. We achieve this objective. The second objective is achieved by connecting a small resistance in parallel. How about this? Does it help in range? Let's try and understand that part. I'll try to understand, but let's try and understand in terms of example. Let's assume a case. I'll give you a numerical example. Perhaps it helps you understand a little better. So what happened? You had a shunt galvanometer. It had resistance G. I have connected a shunt which has resistance of 1 by 99 times of resistance of the galvanometer. So if galvanometer has resistance of 1 ohm, its resistance is 1 by 99 ohms. So this is shunt resistance. And this is the current.
Galvanometer will be 1 by 100, right?
1 by 100. That's what I tried to do. So what is happening? Let's see you understand. I'm just going in the sequence of how do we overcome this limitation. So current I is the current in the circuit, whichever branch I'm connected to. This is the current I wish to measure, but now I have connected another shunt in the parallel. So part of the current goes to galvanometer, remaining part passes through shunt. So if I connect it like this, what will happen? First of all, equivalent resistance will become less than 1 by 99 of initial resistance. It will be less than S. We can calculate that also as G divided by S plus G. Resistance become much less. Second thing, what happened? Current through galvanometer. If the ratio is 1:99. Here, if I is there, what is the current IS? IS will be equal to, current will be inversely proportional to resistance. So IS will be equal to G divided by G plus into I. Okay, and how much that will come to?
99 by 100.
So if ratio is 1:99, the current also will split in the ratio 1:99. Okay. So if the current is 100 units here, 99 units of current will pass through here, and 1 unit will pass through current. Or other way of saying current is I, 0.99 I will pass through here and 0.01 I will pass through here. Okay, and so what has happened now? So when I find this current here is 1 milliampere. If say my range of Galometer was 1 milliampere. So when 1 milliampere is passing through here, I know that whatever current I measure here, actual current is corrected is 100 times. Okay, so 1 milliampere. So wherever I have a reading of 1 milliampere, in place of 1 milliampere, I know actually it is equivalent to 1 milliampere into 100. So what has happened? The maximum current, where the current in the circuit which can measure becomes 100 times more. Okay, so this I could be 100 times the maximum current which can pass through Galometer. So measured current becomes 100 times of Ig if I connect a resistance, a small resistance here. So by connecting a small resistance, why it is happening? Because whatever may be the current, it is allowing a major fraction of current to pass through shunt. Only a small fraction passes through Galometer. If I know what fraction is passing through, I can interpret what is the actual value of current coming into the circuit in the branch. That's the logic behind connecting a shunt. And so in this case, the maximum current that can be measured will increase by a factor of 100. If current measured increases by 100, what will happen? Theta by I. So I becomes 100 times, sensitivity becomes decreases by a factor of 100. So again, to repeat, what is the conversion of Galometer into ammeter involved? Why do we need to make modification? Galometer suffers from two limitation. Range is too small and it has fairly large resistance. We overcome by we convert a Galometer into ammeter by connecting a small resistance in parallel, and that's called shunt to Galometer. With this, effective resistance reduces and the current which can measure also becomes many times more than the maximum current that can be allowed in the Galvanometer. So in this particular case, so what is the equation we're going to use here? See, equation is pretty similar, very simple here. Between those 2 points, what is the potential drop from here to here? G is the resistance and Ig is the current. Ig indicates current flowing through the Galometer. So potential drop from here to here along this path is G into Ig into G, and along this path is equal to Is into S. So that's the only equation I'll use for conversion of Galometer into ammeter. This equation, and in terms of understanding this equation is fairly simple. I'm just equating potential across Galometer and shunt. And this equation can be written in 3 different forms. I can write as Ig by Is is equal to, so this current is small, this current is small, this is large, hence this resistance is small, this is large. And if I apply fraction rule also, if I add numerator to denominator in this side as well as this side, Ig by I becomes S by S plus G. What does I indicate here? The current which is being measured. What is this Ig? Okay, this is current in the Galometer. Okay, and this is the current which is being measured. So this is the only equation. The first, in case of first case, Galometer, torques being equal, and in case of conversion of Galometer into ammeter, only 1 point, potentials being equal. I use that equation, then I can solve anything related to conversion of ammeter into conversion of Galometer into ammeter. Okay. So what is ammeter? So ammeter is not only Galometer. This entire assembly shown within the dotted line is an ammeter. Ammeter is a Galometer with a combination of shunt connected in parallel. And this is the current coming in, which within this it gets bifurcated. By measuring this, I can calculate this quantity. Okay, and this equation. So when we talk about resistance of meter, sometimes you use the word internal resistance or of ammeter. It is a sum of these two. They are two connected in parallel. So equivalent resistance of ammeter is equal to some parallel formula, G into S divided by G plus S. Of course, it will be less than the resistance of the shunt. That's the equivalent resistance ammeter will offer. And S is very small, resistance of ammeter also becomes very small. An ideal ammeter, if X is really small compared to rest of the resistance in the circuit, ideal ammeter resistance is taken to be 0 and potential drop across the ammeter is also 0. That's ideal ammeter. And certain cases we can make this assumption if it is much smaller compared to resistance in the rest of the circuit.
Sir, but resistance doesn't affect the current, right? I mean,
No, you see, basically, let me go to the
we get
previous
a
case.
ratio of the current. So
Yeah, basically, if the current is flowing through like this, moment I connect ammeter anywhere, does it alter I1, I2, I3? Yes, if ammeter has any resistance, it alters the current distribution. The change in current, see, moment if this is a circuit here, if I connect ammeter anywhere in the circuit, either here, here, or here, will the current flowing in the circuit remain same or will it change moment I connect an ammeter?
like
It will change. Only in which case it will not change?
there's
When resistance is truly zero. If not 2 zeros, see, suppose this case is their resistance are in terms of hundreds of ohms. If ammeter resistance is 1 ohm, will it significantly alter the current here? The other resistance are 100 in terms of 100, whereas resistance of ammeter is only say about 1 ohm. Then what will happen? Effect of resistance ammeter being connected in the circuit will not change this value of current much. It will more or less remain unchanged. In that case, I can take the ammeter resistance as 0 because it is much smaller compared to other resistance connected in the circuit. So which current I am measuring? If I connect here, I am measuring I1. Okay, but I1 also, suppose I have taken, if this case, what will happen? I1 by 100 will pass through Galometer. I1 99% of current will pass through shunt. Okay, so what is the range of my ammeter? Range of ammeter may become 100 times more. The current which can measure become 100 times the maximum value of current which can pass through Galvanometer. Is this understood so far?
yes, sir.
Pritam? Pritam,
Yes, sir.
is it easy?
Yes, sir, understood.
So what we are using in this case, we are just equating the potential and we understand this is something, how do we measure this part? And which equation? Very simply, one equation. This equation. What are we writing here? Just equating this potential. Okay. And internal resistance becomes like this, and resistor. And suppose I want to increase the range of ammeter by factor of n. What is the term increase the range of ammeter mean? I am using a term called IG. What does term IG means? Maximum current in Galvameter. Why should be a maximum current in Galvameter? Because that's the current at which it has maximum possible angular displacement. Beyond that, it goes outside the radial range area. So if I don't connect a shunt, this is the maximum value of current it can measure. But if I connect a shunt here, the maximum value current measured is I. So if I want to increase the range of ammeter by factor of n, then this is the current being measured, and this was the current, maximum current which could have measured without a shunt. So I by Ig is equal to n. That's the factor by which I am increasing the range of ammeter by having a shunt. What factor? I by Ig. Is that clear? So what is I by Ig equal to from this equation? I is a large value, Ig is a small value. And in terms of remembering the formula, it becomes easy. What will come in the numerator? Large resistance value and a small one is S plus G divided by S. So this is a simple formula. I don't think you need to remember this formula. It can be easily arrived at from here. Only thing we need to understand factor n, this factor n means this. When we increase the range by factor of n, suppose n is equal to 1000. So whatever maximum current which is allowed in the Galvameter, I can have this current 1000 times more. Okay, so 1 by 1000 is passing through, 999 of 1000 passing through other route. So I made so my range has increased by factor of n. The sensitivity will decrease by factor of n. Sensitivity earlier it was some value, now it will become initial value by 1000. So both are range and sensitivity are opposite to each other. So when I increase the range, of course sensitivity decreases, which you can understand in terms of weighing machine. The weighing machine which has a large range will always have a small sensitivity. Okay, let's try and solve this question now. What is this term here? By our normal convention, this term is nothing but G value. resistance of Galometer, is connected to shunt of resistance, this S value. Current through Galometer is I1. So I1 into G is equal to IT into S. Okay, equating the potential, that's what is given here. So, and current through shunt is I2. And what is the current through combination I3? What is I3 equal to? I1 plus I2. So let's see, what is this given here? I1 into G is given as 100, is equal to I2 into shunt resistance, which is 10. So I1 by I2 ratio is how much? 1:10. But I need I3 ratio also. So what is I1 by I3 be equal to? If this is 1, this is 10, I3 will be 11. Something like this. So if you recall this circuit here, this current, this I3 is coming in here through Galvanometer I1, through shunt I2. So what is I3? I3 is the current is I1 plus I2. So this will be equal to I1 plus I2. So I1 by I3 is 1 by 11. So what is the ratio of I1 is to I2 is to I3?
Sir?
Yes.
Sir, in the previous case, when you said the sensitivity decreases by a factor of n, it's the sensitivity of the whole setup, right, sir?
Yes, whole setup.
Not just the galvanometer.
No, measured current divided by angular displacement.
Okay, sir.
What is understanding? See, this is something, suppose earlier, I was measuring a current of 1 milliampere for angular deflection. Now what happened? See, suppose I connect this S, which is G by 100. When I measure 1 ampere, the reading also, when I mark the graduation on the scale. Now, well, not where I was marking 1 milliampere. Will I still mark 1 milliampere?
No, sir, 100 milliampere.
100 milliampere. So, same angular displacement now, current has become 100 times. So, sensitivity is what? Theta by I.
Yes,
So, if the current becomes 100 times for same angular displacement, sensitivity becomes 1 by 100 times. Okay?
Yes, sir.
What is this question? Has a resistance G is given. Sensitivity is reduced by a factor of 50, which means range is increased by a factor of 50. Range is increased by a factor of 50. What is factor of 50 means? I divided by Ig is equal to 50. What is I by Ig? G plus S. Large value divided by small value. The small value has to be shunt value only, small resistance, numerator, sum of these two. So in terms of, remember, this formula is pretty simple. So this value, so I by Ig is equal to G plus S. We can easily, by value of shunt, we can easily be calculated. 50 is equal to whatever, 400 plus S by S. So these are fairly simple questions, very and fairly, I think, is an easy topic, and it's important topic. The questions do keep coming in various examinations, so it's fairly easy and important topic. I hope all of you find it easy compared to previous topics. And the previous topics also questions which come in the examination are not very difficult ones. If you practice question, you will not have any problem solving those questions as well. So, any query so far on this?